Hey everyone, welcome back to our discussion of continuity. Now, you may have been thinking to yourself, I guess this definition of continuity makes geometric sense, but what's the big deal? Why such an emphasis on it? What more can we do with it? Well, let me tell you. As it turns out, this limit definition of continuity gives us a really easy way to calculate many limit values without having to graph anything at all. The thought process here begins again with a hallmark of continuity, which is that the two limit values, left and right, equal the function value, which of course is the same thing as saying that the overall limit value of a locally continuous function equals the function value. So here's the payoff. If we're given a limit problem dealing with a particular function, and if we know in advance from our knowledge of algebra and foundations and trig, that a function is continuous at the point of interest, then the limit value is numerically the same as the function value. And we don't have to graph anything in order to solve the limit problem. So how can we know in advance that a function is continuous at a point? Well, we fall back on our algebra and precalculus knowledge. For instance, for this fellow here, y equals 3x plus 7, we already know from foundations that he is a nice, straight line. Therefore, he is continuous everywhere. And for any point we pick on this graph, left limit equals right limit equals function value. Therefore, to evaluate this guy, we can simply, without any hassle, fall back on our definition of continuity and write f of 4. 3 times 4 plus 7, which comes out to be a nice 19. I should emphasize that limit values are never conceptually the same as function values, but when we have continuity at the point, then limit values are going to be numerically equal to function values, even though they're not conceptually equal. Likewise, for many other functions, like this big hulking one here, you guys are very much well aware from foundations that this is a polynomial. He is a polynomial boy. And these polynomials, they're continuous everywhere. So no matter what point on them you pick, the limit value at that point must be the same as the function value at that point. Left limit equals right limit equals function value. So stick in 1, seems like I'm going to get, looks to be 0. And this cashes out visually. Again, nice continuous function, left equals right equals function value. Same story for stuff like this. E to the x, 2 to the x, 100 to the x, etc., etc. We know in advance, we know from foundations that these are exponential functions, and that therefore these are continuous everywhere. So the overall limit value exists everywhere and equals the function value everywhere, which a visual serves to clearly validate. So again, here's a nice typical example of an exponential. No matter what point you pick, left limit equals right limit equals function value. However, what if we have another well-known fellow who is known to not behave so nicely, like 1 over x? From foundations, we know that he is not continuous everywhere. However, from the previous video, we know that he is locally continuous everywhere else. And local continuity is all that is required for the limit value to equal the function value at a point. For example, so in this case, function value of 0.001 will equal the limit value by continuity. And let's recap the general shape like so. He's giving us asymptotic behavior right in the middle, a vertical asymptote, so he is not as well behaved as the others. But notice something about any point where he is defined, like 0.001. You take any point where he's defined, then left limit equals right limit equals function value. For 0.001, that x-coordinate, that comes out to be a function value of 1,000. So, it doesn't matter how close the point is to the asymptote, you are guaranteed the existence of a small neighborhood around that point on which left limit equals right limit equals function value. So the overall limit value is the function value. Now, a similar sort of story is going to hold true for the natural log. Even though we know from foundations he has a vertical asymptote at x equals 0, that will not affect the existence of a limit value. For this guy, wherever he is defined, left limit will equal the right limit, will equal the function value, which we can verify visually. Visually, the graph looks like so, just an inversion of the exponential graph. So wherever he's defined, function value will equal limit value. In this case, for e squared, that comes out to be a nice clean crisp 2, positive 2. That's all there is to it. Now, what if we have a function fellow who is not so well behaved? In fact, let's pick a very misbehaving function, tangent of x. We say he's misbehaving because he has infinitely many vertical asymptotes. But those vertical asymptotes only ever occur at odd multiples of pi over 2. Again, we know that from trigonometry. Odd multiples of pi over 2. Everywhere else for any other x-coordinate, the graph will be continuous at that x-coordinate. Left limit will equal right limit will equal function value. Now, is 3 pi over 4 an odd multiple of pi over 2? It is not. Quickly, let us recap the graph of tangent. Looks like so, sandwiched between negative pi over 2 and pi over 2, then pi over 2 to 3 pi over 2, forever left and right. But 3 pi over 4 is not one of those vertical asymptotes. So for any point you pick on that solid peach, any solid peach curve, you will have left limit equaling right limit equaling function value. So that guy, again, that's just what I'm writing here, not an odd multiple of pi over 2. Therefore, we have this guy being simply tangent of 3 pi over 4, which of course is negative 1. And just to put some visual to it, 3 pi over 4 is right there, and the y-coordinate for that point down here is negative 1, and you can see with the green arrows, left limits and right limits equal each other, equal negative 1. And that's all there is to it. And since these ideas are fresh, let's run through a potpourri of problems really quickly. Now, I want you to pause the video, try these on your own, but answer them all conceptually. Why are we allowed to just plug in the numbers? Why? Now, take a stab at them for about a minute, press on pause when you're ready, and we will delve right back into them. So, starting off simple, what is this guy? Well, he's a nice quadratic polynomial. We know something about polynomials. They are continuous everywhere, so this guy is 23. Has a shape like so. Likewise, the limit of the absolute value is just f of negative 4, since the absolute value of x is that nice continuous V shape. Likewise, the limit of that trig boy, sine of x, he is going to be the function value at pi over 2, because sine is a nice continuous wave. Any point you pick on sine, left limit will equal right limit, will equal function value. Finally, for secant, again, I can plug in pi, 1 over cosine of pi, 1 over negative 1, which is negative 1. But why am I allowed to do that? Well, the graph of secant, even though it's not continuous everywhere, it is locally continuous at x equals pi. So just recapping this graph real quick, the graph of secant looks like so. Again, it is discontinuous at odd multiples of pi over 2. But pi is not an odd multiple of pi over 2. It is continuous there, and so the limit value is the function value. You'll no doubt have noticed that every single limit problem that we've done in this video so far has been for a function whose graph we just know off the top of our heads. Lines, quadratic, exponentials, logarithms, trig stuff. But what if we're dealing with a limit problem for a function whose graph we don't know off the top of our heads? Like, let's suppose sine of x over x squared. How do we find the limit of that without having to graph it or trying to do it with a calculator? How do we do it by hand? Well, that brings us to this handy dandy fact here. Almost all of the functions that you dealt with in algebra, in foundations, in trigonometry were continuous everywhere, or they were discontinuous via a hole, or they were discontinuous via some vertical asymptote somewhere. Lines could have holes, polynomials could have holes, a whole host of things could have vertical asymptotes. But key point is that only the truly weird, really misbehaving functions suddenly jumped. Like these. Remember that greatest integer function, the step function from foundations? It suddenly jumps vertically all the time. Then there was that x over the absolute value of x from 2 videos ago. And of course there are all the weird piecewise things you can define using multiple rows. But the only functions expressible in a single row after that equal sign that exhibit vertical jumps are these two up here. The step function, which I've graphed like so, and then x over the absolute value of x, and of course variations on them. and piecewise thing. But again, the first two are the only ones you can express in a single line, in a single row. Well, why is this significant? Well, let me tell you. When you're dealing with functions that can be expressed without the brackets, without piecewise notation, then the only time that the function value won't equal the limit value is for the two weird functions up here and variations on them. For example, the step function, it's always defined at jumps. It's always defined as discontinuities, but the limit values never exist because left limit will never equal right limit. However, for all other functions that you can write without piecewise notation, the function values wherever they exist will equal the limit values. That's because the only potential discontinuities will be holes in vertical asymptotes, and those type of discontinuities, as we've seen, and as I'm drawing down here, never get in the way of a function value equaling the limit value. I'm going to star that step function, and actually I don't have to worry about x over the absolute value of x because the function isn't defined there to begin with. It's really only step functions and variations of them that I have to worry about function value existing but left limit and right limit not equaling each other for stuff expressible in a non-piecewise way. For example, this line up here could be x plus 3 times x minus 2 all over x minus 2. That polynomial with a whole could be something nasty, something whose graph we don't know off the top of our heads. But we know that it does not vertically jump wherever it exists, wherever it is defined. Therefore, wherever it is defined, left limit will equal right limit, will equal function value by that nifty takeaway. Now let's look at some more limit problems dealing with functions whose graphs, again, we definitely do not know off the top of our heads. Let's have a quadratic over a linear up top. In the middle, we got some square root funny business going on. And finally, at the bottom, we got some linear stuff up top with some doubly weird square root business going on down there. Once again, I have no idea how these three functions look like if you were to graph them, but it doesn't really matter. Let's first start with the first one by noting a couple of things. X equaling 5 will not make that function undefined, number one. Number two, this thing does not fit the form of something that has vertical jumps wherever it's defined. Therefore, we can use the takeaway. The function is going to be continuous at x equals 5, therefore overall limit equals function value, and plug on in. Plug that 5 right on in, and what do we get? What gets spit out? Okay, making sure I make no silly mistakes, I get 7. Likewise, just answer a couple questions about the middle one. Does x equal 9 make it undefined? Nope. Does it fit the form of something that has vertical jumps wherever it's defined? Nope. Therefore, the takeaway applies. F of x will be continuous at x equals 9, and therefore overall limit, left limit equal right limit, will equal function value. 1 over 1, which is a nice, crisp 1. It doesn't get any better than that. Finally, same deal. If I stick -2 in that bottom, I don't get 0. I don't get something undefined for my function overall. This thing does not fit the form of something that has vertical jumps. I use the takeaway once again. Function is going to be continuous at the x-coordinate of interest, so the function value is the limit value at the x-coordinate of interest. A square root about down there comes out to be a nice root 4, comes out to be a nice 2, and so we have ourselves a 5. Now guys, notice that in the batch of problems we just did, every single function, even though we had no idea what its graph looked like off the top of our heads, was defined at the x value we were trying to find the limit at. However, let's kick things up a notch. Let's now try to find the limit of functions whose graphs we not only do not know off the top of our heads, but that are undefined at the x-coordinate that we're trying to take the limit at. And let's try to do this without a graph. How do we do this? Well, let's start in a relatively familiar territory. We know that that function in blue from foundations looks like a line. We factor the top, and we know we will have a hole. It's going to be a line with a hole at an x-coordinate of 4. The x-coordinate is 4, and the function f of x looks like so. But now we compare it to the graph of g of x, which is the same graph, except with a shaded dot where the hole is. And that shaded dot has the same y-coordinate as the hole. Therefore, another way we can rewrite this limit is just to get rid of the x minus 4s. Drop the x minus 4s, limit of x purchase 4 of x plus 2 is a nice 6. This illustrates a nice way to find limits for functions with holes at the x-coordinate of interest. all we have to do in this case, for example, is just drop the x minus 4s, cancel them out, however you want to think about it, get rid of them, and the limit becomes a very simple limit of x plus 2, a nice continuous function everywhere. Let's take 2 more examples, and this time let's do it without any reference to graphing. Let's try to find the limit of, say, x squared minus 7x plus 12 all over x minus 3. Factor the top, see what they have in common, cancel them out. This is the same as the limit of that entire line with no hole, x minus 4. That comes out to be negative 1. So there will be a hole in the original graph at 3, negative 1. For this, guys, pause the video and try this on your own and unpause when you're ready. So first thing to notice is that if I plug in 3/2, I'm going to get division by 0, which will make this function undefined. Just like in the last problem where I'd plug in 3, I'd get undefined. And in the problem before that where I plugged in 4, I would also get undefined. Now, I can actually factor the top, cancel, and I get a nice limit of the whole line, x minus 1, comes out to be a positive 1/2. Therefore, in the original, my hole will be at 3/2, 1/2, and the hole up top was at 4/6. By the way, guys, remember, any time stuff cancels, variables cancel, holes will happen. That's what I'm boxing here in purple. Holes happen when things cancel. Holes do not have to happen only with lines. As you know from foundations, they can happen with virtually any shape. All that's required is a variable in the top to cancel with a similar variable in the bottom. For example, let's try this guy for size. Try them on for size. X minus 3 over the square root of x plus 6 minus 3. The limit as x approaches 3 for that. Notice 3 will make this thing undefined. And the way you handle roots for holes is to multiply by the conjugate. That's why I've changed the plus signs to minus sign. We call this the conjugate of our radical expression. And let's see what we get. We get an x minus 3 times some stuff up top. Got to be very careful when you're following the bottom now. You'll have 4 terms, but those middle 2 terms will go to 0 always for conjugates. So at the top we leave as it is. Leave the top as it is. Don't try anything funny with that. But the bottom simplifies to a nice, aesthetically pleasing x minus 3. Cancel. We are going to have a hole, ladies and gentlemen. And that hole will be at the next coordinate of 3. And I just have to take the limit of this much nicer radical expression. Plug in 3. It'll give me 6. And I have a hole at 3, 6. So if you want to graph this, graph the plane square root of x plus 6 plus 3, and then just put a hole at 3, 6. And that's if you want to graph it. But again, you don't need to graph to do these problems. Now let us turn our attention to one more type of limit problem for an x coordinate that makes the function undefined. These first 2 problems are the problems we just did. We saw that 4 and 3 made the functions undefined, but that did not stop the limits from existing. However, that's not always going to be true. Take this guy. It turns out this limit does not exist. 4 makes the function undefined, and the limit is undefined. The limit also doesn't exist. Why? Why does it not exist? Well, we have to recall something from foundations. If we have an x-coordinate c, and we plug it in and get 0 over 0, this could indicate a hole. Sometimes it indicates a jump, but most of the time it indicates a hole at x equals c. However, if we plug in an x-coordinate and we get a non-zero number over 0, which is what would happen in the problem we just wrote, if we plug in 4, we get 1 over 0, this indicates a vertical asymptote at x equals c. And vertical asymptotes, in the language of calculus and the language of limits, are places where limits don't exist, either left or right. So visually, if we have a vertical asymptote at an x-coordinate, the limit can never exist there. We've seen this multiple times with many graphs. Let's take another one. Say I have this little fellow here. Vertical asymptote. Notice both left and right limit for the x-coordinate of c do not exist. They're both positive infinity, which is just a more specific way of saying how they don't exist. They don't exist. So again, in the case of this, if I plug in 4, f of 4, I get a non-zero over 0, 1 over 0. This indicates a vertical asymptote. And by the by the pink star, the limit cannot exist there. By the way, if you're curious to know what this graph looks like, it looks a little like so. It's never defined to the left of 0, and it has an asymptote at x equals 4. Left limit goes to negative infinity, right limit goes to positive infinity. They both do not exist. So very, very important to remember this stuff in pink, the star and the box. Now, my friends, let's end on a fun note. Let's end with oh my. Oh my. Oh my, oh my. Look at this mathematical delight. If you can do this problem, then you understand this video very, very well. This is a dangerous boy. Now on to the problem itself. And look, unless you're a very special person, you ain't got the foggiest idea what the graph of this thing looks like. Actually, I lied. If we plug in 0, do we get non-zero over 0? Not at all. We get 0 over 0. So at the very least, we know we don't have a vertical asymptote at x equals 0. It's either a hole or a jump. Now, I don't know about y'all, but when I see a lot of x's, that triggers something in me that makes me want to factor stuff. I can do the top like so, pull out an x to the 4th, leaving 8x squared minus 3 in the inside. And I can do the bottom like so. I can utilize my root properties. Well, before that, I can factor the inside, x to the 8, pull that on out. And then I can use root properties to break that up into 2 roots. I can break that big root into 2. But there's something more we can do with that square root of x to the 8th. Well, before that, I suppose I can now write this like so. Like so. And then the key player, that square root of x to the 8th power, I can do something more with him. Recall that from an earlier video, that in the world of functions, the square root of x squared, which I'll denote here in gold, is the absolute value of x. That's how it's defined in the world of functions. Well, just building off that idea, if I want to take the square root of x raised to some higher power, again, in the world of functions, let's say x to the 4th, well, that's the square root of x squared squared, which in the world of functions is the absolute value of x squared. You can see that denoted there in pink. Likewise, x to the 6th, write that as something squared. That something is x cubed. That x cubed is what gets absolute valued. I don't know if that's a word, but if it's not, it should be. Anyway, the square root of x to the 8th, I can write that as square root of x to the 4th squared. And there we have it. Square root of x to the 8th in the world of functions, which is the world I'm dealing with, equals the absolute value of x to the 4th, which thankfully, since x to the 4th is being raised to the 4th power, it's an even power, I can drop the absolute value symbol. It's an even power. Now then, this has the pleasant effect of changing that entire fraction, that entire brown beach sand star, into an x to the 4th. And look, stuff canceled, i.e. we are going to have a hole. We're going to have a hole in the original at x equals 0. We are going to have a hole there. Now then, using previous ideas, I just move on forward with my limit process, but pretend I'm dealing with the function that doesn't have a hole. That function that doesn't have a hole is this guy here in what color? Oh, let's go with gold again. I like this gold and red. For some reason anyway, this guy notes he has no vertical jumps. He has no hole at x equals 0. Again, this guy in gold has no hole. Not the original. The guy in gold has no hole. He also has no vertical asymptotes at x equals 0. Therefore, we apply that takeaway from a few slides ago. He is continuous at x equals 0. So the limit value is the function value, and we throw on in a 0. We throw that 0 right on in, and we get I believe the mathematical gods are telling me that this is a negative 3 over 1, which is a negative 3. I'll circle that in violet. And again, don't lose sight of the geometric stuff, graphical stuff. That means we have a hole at 0, 3, negative 3 in the original. Likewise, don't lose sight of the graphical stuff. The denominator of our original equals 0 when x is 1 or negative 1. It also makes the denominator of the golden box 0, but it doesn't make either numerator of the original or the golden box 0. It's non-zero. So we will have vertical asymptotes at x equals 1 and x equals negative 1. I must say, I like the color scheme in this. It's like watermelon with some, I don't know what you call that, red and gold, but it rubs me the right way. We get this shape here for our graph, a hole at 0, negative 3. It's like a parabolish shape, but it's not a parabola because it doesn't grow unbounded. It is stuck between negative 1 and positive 1. But you can see left limit equals right limit equals negative 3. That was lovely.